lecture 11B for Calculus 2. Actually, it's 11C for Calculus 2, and it is on the series, infinite series, in terms of partial sums, the integral test, and on linearity. So on this slide, I'm just going over partial sums again, and I'm mentioning yet one more time about the notation change. Again, math, I think I said it before in math. Notation in math is equivalent to a sketch in engineering. If you have your notation right, a lot of times the solution is apparent. If your notation is wrong or it's sloppy or confusing, you're going to struggle. So let's look at this notation yet one more time. The index n is used in two ways here, right? If you're just talking about the series itself, it's a counter for the terms. Where's the highlighter? It's a counter for the terms, okay? That's all. In the partial sums, n is the counter for the partial sum, but then in terms of the summation sign, it ends up being at the top of the sigma as the maximum number of terms that you're going to add up to create the partial sum. So a partial sum, s to the n, is the sum of the first n terms of the series. And now if you look at the limit, as n goes to infinity of those partial sums, they will make a sequence. If you look at their limit, if it converges, is the limit also of the original series. So what we're going to do is take a bunch of terms, a series. We're going to add up, say, the first, the second, first two, the first three, the first four, the first five, the first six, etc., and we're going to look at where those sums go. If they converge, that is what the that's what the value of the sum of the that's what the value of this infinite series is. This is a good example of this partial sum in case you don't have a good picture of it yet. And what I'm demonstrating here is that any method that you use to test the convergence of any sequence can be used to test the convergence of these partial sums. So you could use comparison tests, L'Hopital's rule, squeeze theorem, etc., etc. Here we're going to use observation, right? And then we're going to look at this series, n equal 1 to infinity of 10 to the minus n. Let's look at the partial sums. S1 means we add the first one term, and so that's 0.1. Now let's add the first two terms for S2, and we get 0.11. Add the first three terms, and we get 0.111, yes. And for the nth term, so we're going from k equal 1 to n of 10 to the minus k, and that finite sum is 0.11111 all the way out to n terms. That's n of them. Okay. So let's use the monotone test to determine the convergence of these partial sums. Notice that the sequence of partial sums is strictly increasing. The next term is the previous term plus 10 to the minus n plus 1. And it's always greater than the previous term because this is positive, right? So you're taking s to the n and adding something positive to it. Obviously, you're going to get a bigger number. It is bounded from above. That least upper bound is 1/9. So by the theorem of bonded monotone sequences, this sequence of partial sums converges to its least upper bound, which is 1/9. Therefore, the series itself also converges to 1/9. And that's what's written here. Okay? Of course, remember 1/9 is 0.11111 forever. We have a theorem here for the series itself, and this is for the special case of non-negative terms. Let's say all the terms a to the n are all greater than or equal to 0. Then the series converges if and only if the partial sums are bounded from above. And the one we just did for the 1/9 was an example of that. But if and only if means if you have non-negative terms and the series converges, then the partial sums are bounded from above. On the other hand, if the partial sums are bounded from above, then the series converges. If and only if means that the A implies B and B implies A, where A in this case is series convergence and B is partial sums being bounded from above. For the integral test, remember that when we first studied integration in semester 1, the integral was represented by a sum, by the sum of the areas of rectangles. we can compare a sequence to a real valued function. So if we compare the sequence to a real valued function, when we start adding up the terms of the sequence, we are in effect integrating that function. All right, let me draw a picture of that for you. So here's our coordinate system, and now here's our terms. It's here, 2, 3, 4, 5. Let's say it's like that. And of course this is 1, here's 2, here's 3, 4, etc. So this is the domain being discrete, 1, 2, 3, 4, 5, and here are the values of that function. Now, if this was a Riemann, if this was a real valued function, and let's just say that maybe it has a constant value right here. Alright, I'm going to connect all these. There's going to be little jumps in them, but okay. Well, there's more than jumps, there's shakiness. I could try to do it again and make a bigger mess. Alright, so instead of just having this little function, these little values here, I'm going to now integrate under this curve. Okay, so if I integrated, I could take the value of the function at 1, so it'd be the function at 1 times the step size here. But what is the step size? It's 1. Plus the function at 2 times the step again, which is 1. So you see that looks like f1 plus f2 plus f3. And I would get the same value if I added those values at a to the n, and here just say going from 1 to 4. The next term here would be f4. So by adding the terms of the series, by adding terms of the sequence, creating the series, we are in effect integrating over a real valued function that looks like this. Right. Now since we're going to infinity, this integral, which actually in the limit I could write it as an integral from 1, in this case I'm just showing 4, but if we want to continue forever, this would be an integral from 1 to infinity of f of x dx. This is an improper integral. Remember, you've got the upper limit is infinite, so you have to replace that with a variable such as a, and then take the limit as a goes to infinity. Okay, so if this improper integral converges, then the series converges. If it diverges, if the improper integral diverges, then the series diverges. The only caveat here is what I've drawn would be the same if you made little steps. Okay, but if you replace this function with some those points with a function, some decreasing f of x function, then you wouldn't get the same value. They would both converge, but the integral, that improper integral, would converge to a different answer possibly than the series itself. If you use these little steps, then of course you have a numerical problem, and you haven't achieved anything because you can't integrate that in a kind of closed form solution. It is just a numerical integration. In fact, it is exactly the same as your original problem. Now this is the linearity property of convergence, and it looks like the linearity property for limits, and it is because the convergence is actually a limit. If you have a sequence, if you have this series and it converges to L, and you have a series of terms bk, okay, and it converges to M, then any linear combination of these two series converges to C. I guess I use C here instead of A. C times L plus or minus D times M ends up being a linear combination of the two limits. Here's an example. It's slightly artificial, of course, but just for demonstration purposes. Here's my first series, 1 over 2 to the n, and it converges to 1. Its sum is equal to 1. Then I have minus 1 to the n over n, and it equals 0. This infinite series equals 0. So I would like to know what is the sum of these two together. Like I say, this is a little artificial. Ordinarily, things would be buried in some algebraic concoction, and you'd have to, sort of tease them apart to get your two sequences that you could then apply the theorem to. Right? So, but I'm going to use this linearity property right here. Here is my sum over these two sequences. Right? What can I do here? I can break it into two pieces. I can factor out the constant terms. All right, and then when I look at, I have this isolated, the first series isolated, and now I have the second series isolated as well. And the answer is the linear combination of the two limits, so 7 times 1 plus 0. And so that limit is 7. Like I say, this is a little artificial because all I did was put the two series together, which is so obvious how they come about. But that's a linearity property.